but just coordinate that beforehand if you would. All right, first things first. Go down here. All right, looking at our schedule, let's go up here. Again, hopefully today we'll finish Module 1. Got a number of things we're going to do. Got a video or two to watch. If we get to the Quizlet, we'll do the Quizlet. I don't know if we'll get there yet, but we'll see. Finish up the notes, finish up the PowerPoint, and we'll be ready, hopefully, to finish all of Module 1 today. Last night, 6A was due by midnight. Make sure, I think everybody got it in. If you haven't got it in, I think I talked to you. Other than that, your Module 1 notes are due for Monday's class. Okay. And I'm hoping it's easy because, I mean, I'm going through all the notes and pretty much giving you all the answers. All you got to do is write it down. So that's kind of the idea behind those things. All right. So I do have, let's see. That's the next thing that's due is that Module 1 notes. And again, just download them, edit them as a Word document, and post them right here. Post them back to the assignment. You have your Module 2 notes. So again, the 28th will start there, and that the Module 1 are due. Next Wednesday, you have your first quiz, which will basically cover all of Module 1. I don't think I'll do anything on Module 2 there. So just go back and review Module 1 for between now and next Wednesday. And then the next Monday, again, we're off. But we'll finish Module 2 then, and then the week later we'll start Module 3. Module 2 is basically heat transfer and the Earth's energy balance. Module 3 is water cycle. And then hopefully the 11th we'll finish up everything. Your Module 2 notes are due by midnight on the 10th. Then your Module 3 notes will be due on the 18th. And that test will cover all 3 modules. Okay, and so we'll talk about all of that. All right. Questions about scheduling and where we're due and who needs to do what to whom and so forth and so on. We're good? Okay. All right, let's press on. I was looking at my email, had a NBAA, which is National Business Aviation Association. You guys as students can get, I think for like $30, a membership to NBAA. Now, what does that get you? It gets you onto their job boards. Okay. And it's a national, business aviation association. So, I mean, it's got a ton of information. I use their templates for my aviation management class, how to write an operational plan, this, that, and the other that, FAA requires. So there's a lot of stuff on that website that is useful. So, as a student, I give you a number of Margot, who's the assistant vice president for recruiting. If you're interested, like I said, $30, and then you get access to all of the NBAA stuff as a student. It's a pretty good deal. If you are interested, just let me know and I'll give you that number. All right, next. So the article I got, this is actually off of AvWeb, which is a little different, but that's okay. I get AvWeb. You guys can get AvWeb. But this weather accidents, okay, I'm not going to go over the whole thing, but basically it says, hey, what a country. We probably have the best weather detection and forecast system in the world. But what happens? People still crash because of weather. Why? Because number one, forecasting is not an exact science. Even observations, isn't an exact science, and weather changes all on its own. Crazy. Anyway, so they take a look at a couple of accidents. One because of um, a Cessna 182 in Abilene, wind accident, and then another one here, Cessna 210 from New Mexico. And so they actually take a look at those accidents and just take a look at what you can learn from those accidents. This is a reason we look at accidents. We need to look at what other people mistakes they make so we don't make those same mistakes. Okay, and so I will routinely watch videos on weather accidents and get articles and stuff like that. I just posted this to Moodle this morning, so take a look at it, see if you can take anything out of it. Really quickly, make sure I got the next thing. On the notes, let's preview where we're at on the notes here. There it is. That's PowerPoint. Very quickly. We've pretty well, it would be nice if I didn't put the navigation one there, wouldn't it? Okay. It would be 111. That's the one I'm looking at. Okay. There we go. Maybe I'll even get the right one up there. All right, so we have looked at, just as a review, size, definition, characteristics of the atmosphere, right? Mainly, we're talking about the 4 primary layers and the composition. Composition of the atmosphere is 78%. If you've got your notes, you should already have this down. 78% nitrogen, 21% oxygen, about 1% argon, and itty bitty percentage of other gases, CO2 being the 4th primary one. So there's the top 4 gases and their percentages I just gave you. And how are the atmospheric layers defined? And we said that was by what the temperature does in that particular layer. So we know in the troposphere, temperature drops until you hit the tropopause. Then when you get into the stratosphere, the temperature goes back up because it's absorbing UV radiation in the ozone layer. And then when you hit the mesosphere, the temperature again drops drastically down. And then as you start getting outside the atmosphere into the thermosphere, the temperature again goes up now drastically. And in between each of the layers, there's a pause, tropopause, stratopause, and mesopause. Okay, so definitely know that. Know the function of each of the top 4 gases. Okay, the main thing is nitrogen is non-reactive. So nitrogen gives our atmosphere its stability. Okay, oxygen feeds us and feeds life, and also supports any burning. Okay, any fuel. So a lot of the oxygen is really important. CO2 provides gaseous food, if you will, for the plants, right? And then they convert it to oxygen. And then argon basically is neutral. So again, it provides stability to the atmosphere and volume. And the other one is the weather comes from the water. About 4 to 5% in volume is what the atmosphere can hold. And the definition is, what is the atmosphere doing at a specific time? And we know that an air parcel is basically a 1 centimeter parcel of air, and we define weather as what that parcel is doing. Is it rising? Is it falling? Is it staying neutral? Okay. And so I would know the characteristics of each of the layers we talked about, and that was all there. And 2 videos we watched to do that. We talked about the standard atmosphere. If I ask you to do a calculation in the standard atmosphere, is everybody okay with that? Okay. We know that most of the ICAO chart is a ratio, right? Or like a density ratio, pressure ratio. So be able to pull off information off of that ICAO chart if I ask you to do that. And okay, I would definitely know in Handbook Chapter 8, we talk about atmospheric pressure. I think I'm going to pick it up. I got a video we'll start with here. And it will actually pick up on atmospheric pressure. So let's do that. Where's that video? Video's right here. Okay. We're not going to watch this whole video. We'll watch about from 6 minutes. What is it, 6:30, I think? Yeah, 6:48 to 17:35. So we'll watch about 11 minutes of this video. Okay. Here it goes. Okay, back was said 6:48. Okay, let's see. Let me share that video with you. Chapter 6 YouTube, and it's gonna pick it up at atmospheric pressure right here. So let's do that.
Atmospheric pressure, or the concentration of air molecules over a given area, is measured in terms of inches of mercury, or millibars. 1 inch of mercury is equivalent to approximately 34 millibars. The measurement of pressure is done with the use of a barometer. This instrument is nothing more than a partial vacuum within a glass tube containing mercury. As the pressure of the air exerts a force on the container of mercury, the mercury will rise. The average atmospheric pressure of the Earth will make the mercury rise 1,013.2 millibars, or 29.92 inches. This measurement is considered to be standard pressure. During periods of higher atmospheric pressure, the force exerted upon the mercury is greater, which forces the mercury to rise. The reverse happens during periods of lower than standard pressure. If we imagine standard air pressure as a plane, we can visualize the relationship between air masses with different densities. On the left is a high-pressure system, or a mass of denser than standard air. It is more dense at the center of the mass. On the right is a low-pressure system, or a mass of less dense air. Pressure changes occur more rapidly directly between the center of the high and the center of the low. As we rotate the image to a top view, we can draw lines around the areas that appear to have the same height, or in this case, the same amount of atmospheric pressure. These lines are called isobars, and they are drawn on weather maps to represent areas of equal pressure. By using these lines, you can determine the position of high and low pressure areas. You can also tell how large or severe they are by the number of lines and how they are placed. Notice how the isobars are closest together directly between the high and the low. The closer the lines, the stronger the pressure gradient. Air from a high-pressure area will flow directly toward a low with a force which relates to the pressure gradient. If the Earth didn't rotate, highs and lows would exchange wind directly in this manner. However, Coriolis force from the rotation of the Earth is also acting on these systems. As winds spill off a high-pressure area in the northern hemisphere, they are deflected to the right. This results in a clockwise flow around a high and a counterclockwise flow around a low. As the wind is driven around these systems, the air closest to the surface is slowed by the friction of the ground. When this happens, the Coriolis force is diminished until the pressure gradient force becomes greater. The resulting wind tends to flow across the isobars toward areas of lower pressure. At altitude where airflow is not affected by the surface friction, the wind continues to flow parallel to the isobars. In addition to creating large patterns of wind around highs and lows, differences in atmospheric density can cause wind flow on a local level as well. In areas near the ocean or other large bodies of water, local changes in heating and atmospheric density can cause daily wind flow patterns. During the day, water slowly absorbs heat. On the nearby land, the sun's radiation only penetrates a few inches into the soil. The land surface heats up much quicker than the water. As the air over the land warms up and begins to rise, air over the water is being cooled down because of the cooler surface of the ocean. The cool air then flows inland to replace the rising warm air. This produces a sea breeze flowing inland from the ocean. During the night, the land cools very quickly. The air above the landmass begins to cool and sink. The ocean, now warmer than the land, begins to warm the air above it, causing the air to rise. The flow of the cycle now reverses, and in the evening, a land breeze will be experienced. Local wind patterns can also form as the result of mountainous terrain. One of these is a foehn wind, which occurs when there is a mass of cold, dense air near the top of a mountain range. As the air pushes over the top of the range, the cold air begins to descend down the other side. As this air accelerates and replaces the warmer air beneath it, it begins to compress and warm up. As the air heats, it will eventually become warmer than the air it is replacing. This causes the atmosphere at the bottom of the hill to become warmer. These winds can become very strong, with gusts exceeding 120 miles per hour. In the Rocky Mountains, they are called Chinooks. In the Sierra Nevada mountains, they are the Santa Ana winds. Regardless of their names, these winds can produce large amounts of damage and are hazardous to aircraft, both in the air and on the ground. They can occur during what would normally be perfectly good VFR weather, and is one of the reasons surface wind reports are important to you when receiving a weather briefing.
About that wing.
We have seen how heating and the differences in air density can produce wind. The other major force in the formation of weather is moisture. Moisture occurs on our planet as a solid, a liquid, and a gas. Within these states, it can take many forms. We see moisture as clouds, as rain, hail, or as snow, ice, or water. Dew and frost are also forms of moisture. How water changes back and forth from state to state is very important to the formation of weather. We have all experienced the effects of evaporation, such as water evaporating from a lake. When water turns from a liquid to a vapor, the process requires heat. This heat energy is drawn from any available nearby source and is stored by the vapor. When the water vapor is returned to a liquid through the process of condensation, the latent heat that was stored during evaporation is now released. The heat exchange during evaporation and condensation is a major factor in the vertical movement of air columns. Thunderstorms, for example, can be developed by this force. Originally, the air begins to rise through a force such as the sun heating the surface, which in turn warms the air above it. As this warm air cools and eventually condenses, the latent heat released from condensation will, under the right conditions, continue or increase the strength of the updraft. If this process continues, a thunderstorm can develop. In vapor form, molecules of water exist between other molecules contained in the atmosphere. When the air is warm, more room exists between the molecules of air. Therefore, more water molecules can squeeze between the air molecules. When the air is colder and the air molecules are closer together, less water vapor can fit between the already close air molecules. For this reason, cold air cannot hold as much water as warmer air. Dew point is the temperature at which an air mass becomes completely saturated with water vapor. In other words, it will hold as much water as the temperature will allow. When an air mass becomes completely saturated, condensation occurs. Let's say that we have an air mass with a temperature of 55 degrees Fahrenheit. If the dew point is also 55 degrees, then the air is 100% saturated. If condensation nuclei are present, then condensation will occur. Clouds, fog, and dew are all forms of condensation. When water that is formed on the condensation nuclei becomes too heavy for the atmosphere to support, then precipitation occurs. Since the moisture content in an air mass is relatively constant, the air mass must usually undergo some form of cooling in order for condensation to occur. For example, if the air is 50% saturated at 55 degrees, then the air must be cooled to about 37 degrees in order for condensation to occur. When the temperature reaches 37 degrees, this air mass will be 100% saturated. Weather is something that we must deal with daily as pilots. It is constantly changing and infinitely complex. Knowing the basic driving and manipulating forces of our Earth's weather patterns will help you to understand the more detailed conditions and concepts that will be introduced in the following weather sections. Being able to understand the concepts of weather development will not only help you understand the current conditions, but will also help you anticipate future changes as well.
Okay, we'll stop there. Let's see. We have already seen that, and I'll go back to the PowerPoint in a minute. Let me preview this. We're going to talk again about global circulation. We know that if the Earth wasn't rotating, we would basically have two cells in the northern or actually one in the northern and one in the southern hemisphere, but that's not the case. Because of Coriolis effect, we know that we have a basically 6-cell system, 3 north and 3 south. And each one produces its own pressure at specific latitudes. Okay, and we'll talk about that a little bit more. Let's see, that looks like right there. And then we'll talk about how winds are described. We talked about that a little bit yesterday. We'll talk about it more. If, for example, I said winds are 050 at 10, and you were flying into Moore County Airport, which runway would you expect to take? Runway 5. Okay. If I said winds are 230 at 5, you would, yeah. That's why they describe the winds in that manner. Okay, they're going to match up with your runways. Okay, then we'll talk about local circulation, sea breeze, land breeze, valley breeze, mountain breeze. Those were actually in your exercises for, it looks like they talked about it. Those are specifically in your 6A reading. Speaking of which, let's take a look at it real quick. If you can pull up your 6A, do I have it here someplace? I do someplace. Thought I opened it. I guess I didn't. All right. Oh yeah, I did. Hang on. There it is. Here's the 6A. All right. I'm gonna get that to come up. Okay. Needs to go in. Somehow I got it pulled out. Let's see. There we go. That's what I wanted. Okay, I got to put it back in there. Let's take a look at the 6A exercises real quick. Okay. Everybody okay with the 4 layers? Okay, troposphere, stratosphere, mesosphere, and thermosphere. Everybody cool with that? Do you notice something about the troposphere on this picture, though? Huh? What do you notice on that circle right there? So at the equator, is the troposphere higher or lower than at the poles? Much higher. And in fact, the troposphere will in fact rise and fall with the seasons. Why? Because colder air is dense. So in the wintertime, the troposphere even locally will come down some. Okay, but it'll normally fluctuate between 25 and 30,000 feet. But there will be a fluctuation seasonally for the troposphere. Where is most of the weather contained? We know. And why? It's the only layer with moisture, and the weather basically comes from um, the moisture in the air condensing, right, or evaporating, or staying as a liquid. You know, those are the reasons we have weather. Okay, anybody want to describe the atmospheric convective process? What creates convection? Go ahead, Ian. Uneven heating, yeah. And what that does is create variations in density in different locations. And so when the air is less dense, which way do it go? Yeah. And then it will displace the air above it. And then when it cools off, it'll come back down. And now you have a circulation pattern. Okay. And you can have global circulation patterns and you can have local circulation patterns. Okay. Um, and what's the primary cause of changing altimeter settings? If you guys have that, take a look at that. Say it loud. Okay, so everybody got that? Okay, cool. And closely spaced isobars. We know iso means same, bars is barometer or barometric pressure. Okay, isobar. So when you see it on a map and it's close together, okay, what's going to happen with the wind? High or low winds? High. Why? A greater pressure gradient or greater pressure difference. So yeah, you're on the right track. Okay, everybody cool with that? All right. What factors affect the deflection caused by Coriolis force? Latitude's one of them, right? Mm-hmm. The higher you are, the more the Coriolis effect. What else? Say it loud. Okay, speed and distance. Yeah, that was in the reading. Everybody got that? Okay, cool. And frictional force. Why is it you get a shifting in your low level winds and your high level winds? The big F, right? Science F word. Y'all ever heard of the science F word? It's not four letter. Yeah, it's friction. Okay. Yeah. Science F word. It's a frictional force basically, and I showed you yesterday. The upper level winds will move basically straight, whereas the lower level winds, because of friction, will slow down, and so they will curve with the Coriolis effect even more. Okay, so you'll get the deflection at the lower levels because of friction. Okay, because there's going to be a difference in speed in upper level winds and lower level winds. We saw that if anybody was following the Weather Channel for Hillary coming ashore in California, one of the things they were saying a whole bunch was that the lower elevations, would get some wind, maybe 30 to 40 knots of wind. The upper elevations would get almost hurricane force winds. Why? There's no friction to slow it down. So when those winds hit the mountains, they were much, much higher. So we actually saw that. Okay, which one of these is a sea breeze? Day or night? Day. That's why you go to the beach in the summer. You got that nice sea breeze coming in, right? Sit on the beach under your umbrella, kick your feet up, do a little skimboarding or belly boarding, whatever, a little surfing, having a good time. Yeah. But you'll notice even down here at the beach, once you come across the bridge, it's hot, right? Right? I mean, if you're on the beach and you're sitting there, you got a nice cool breeze coming off the water during the day. As soon as you come across the bridge, that thing's gone. Okay? We'll talk about that. You'll also notice probably the sea breeze around 6, 7 o'clock, 8 o'clock in the evening, all of a sudden, boom, no breeze. Where'd the breeze go? Okay, that's because the temperature of the water and the temperature, and we'll talk about it specifically a little bit later, but it's the difference in the temperature of the land and the water that causes the air to rise over the land, right, during the day because it's hotter. In comes the creates low pressure. We know low pressure sucks. Pulls the air in from the water. The thing about it is the land will heat up. It has a much lower, what's called specific heat, which the definition of specific heat is how much energy can a substance absorb and have a specific rise in its temperature. Does that make sense? Water can absorb tons more heat, and the temperature may go up 1 or 2 degrees. Okay? And if the land absorbs the same amount of heat, it may go up 20, 30 degrees. So now you have a 20, 30 degree difference between the land and the sea. Well, if it can take in that heat and the temperature goes up really fast, the opposite occurs. Okay? The water will not, the temperature won't change all that much at night, maybe a degree. Whereas the land, the temperatures will again go down 20, 30 degrees, especially if you've ever been out in the desert. 90 degrees during the day, 20 degrees at night. All right. And so now, over the land, it's cold. So what's the air doing? All right. And now the water's warmer. So where's the air there going? And so now it's sucking air back out to sea. So you get the land breeze, and it's a cool breeze, well, relatively cool, okay, at night. And it usually hits about, 3, 4 in the morning. All right. Well, what happens when the two temperatures are equal? What happens to that land or sea breeze in that transition period? Nothing. Exactly right. It stops. Okay, you're not getting a temperature differential. You're not creating a circulation. Okay, so that's the land and the sea breeze during the day and night. All right, if I'm in the mountains, which is going to warm up first, the peaks or the valleys? Which one's going to get the sun first? The peaks, okay. So now the peaks are warmer than the valleys. Which way is the air going? The other down. Okay, Marine Corps down. All right. So yeah, what you get is at the elevations, what's the air going to do when it warms up? Rising, and it's going to suck the air up from the valleys. Okay. All right. And then the opposite's going to happen at nighttime when it cools off. The air up here is going to get heavy, and the wind's going to go down the valley. Okay. So you get valley breezes and mountain breezes, and dadgummit, if you're not careful, if you're doing mountain flying in a small airplane, that type of winds will get you. All right, will blow you right down onto the mountain. All right, so you got to be careful and watch your flying around high terrain. Okay, so we'll talk about that even more. All right, everybody cool on the exercises? I hope everybody got them in. I think everybody did. By the way, I think I graded them if you did turn them in. Most everybody got 100. Y'all did a good job on it. All right. All right. All right. If you've got your notes, we'll finish up the PowerPoint. We're doing pretty good here. Let me find the PowerPoints in here someplace. There it is. All right. There you go. Okay. So we've hit all these, their partial structure, troposphere, stratosphere, mesosphere, thermosphere, exosphere. I'll just hit that again. Be able to do a calculation off the ICAO chart with the standard atmosphere. We talked about atmospheric circulation yesterday, and the wind again, we'll pick it up here. The wind again is movement relative to the surface of the earth And the forces, again, that affect that are the pressure gradient, right? How much pressure change you have, Coriolis effect, and surface friction. Talk about that. All right, this again, global circulation with no rotation of the Earth. You've got the two-cell model, okay? But because you've got the rotation, then you have the basically three-cell per hemisphere model. Make sure you know the Hadley, Farrell, and polar cell. You can also call out the mid-latitude cell. I guess I've seen both. And you need to know what's happening. Down here, you've got a low pressure system, so what's the weather going to be? We understand. Yeah. Okay, remember, anytime you have air that's rising, you're going to get an unstable atmosphere. Okay? Right here, the air is descending, right? So at the horse latitude, you're going to have basically good weather the whole way through the wind. Because you notice the winds are changing direction too, right? They call those the doldrums. Right? Okay.
So where Hawaii is, right? But it's relatively calm.
Well, Hawaii, I believe they are there. I want to say they're about. Somebody look up the Latin law of Honolulu. I think it's about 20. Shouldn't be that much. Yeah.
I remember seeing like I was joking about satellite, like all the bands.
Yeah. Jeff, what's the latitude of Hawaii? I think it's in the 20s. Call that, okay? Yeah. So you're still 10 degrees south of your horse latitude, so that's why you get your northeast trades. Okay? This is why the north part of the islands are wet. Kauai actually, I think, has the highest amount of rainfall on the north side of that island. And you get these real heavy tropical rainforests on the windward side of the islands. But on the leeward side of the islands, like where Lahaina is right now, they're in what's called a rain shadow because the mountains, basically what the mountains make orographic lifting, make the clouds go, or the moisture rises and it dumps all the rain on that side of the island. Okay, guys? You're looking at my stuff, that's cool. Okay. All right, everybody cool with this? All right, good there. Atmospheric pressure we just talked about. Everybody definitely know the standard pressure. Know it in inches, millibars. Okay. Know it's 2992 inches. Definitely 1013.2 millibars and 14.7 pounds per square inch. And I would also know that on a map, the lines of equal pressure are connected, are called isobars. If they're close together, you have a high, you have a high pressure gradient, so you're going to get lots of wind. If they're far apart, not so much. Pressure gradient is, the change in pressure is spread out. So, okay, so you can see right here, you know, up here, and they're going to have much wind. And here, it's going to be windy as anything. Okay, so that is, I mean, just looking at, by the way, this is a surface analysis chart. Just looking at this, I can tell you what the weather is all over the place, pretty much. But if you learn the characteristics of cold fronts right here, it's getting cold front. Okay, and it's moving in this direction. Now, how do I know that? We have bars, okay, and it's 2 and 20. Right here is a stationary front. Okay, it alternates warm front, cold front, and one is trying to get out the other, but it's not winning. You know what I mean? Okay. Right here is specifically a warm front. That means the warm front. Okay. And we're going to learn the characteristics of each of those fronts. Okay. Typical of a cold front is, I'm getting off the rabbit trail, is typical, makes air rise real fast. Okay. And so it's not going to be very wide, but it's going to be pretty violent. Up here again, you've got the center of the low pressure system. So in that area, you're going to have probably a combination of warm front, cold front, and cold. But you can tell right in here, you're going to have some cold front there. Stationary front kind of acts like a warm front. It's not near as severe. You don't get the rising of the air. And so basically get light rain. Same thing for a warm front, basically stratus clouds and light rains. Okay. But we'll look at all that. So I mean, I can just leave that. Kind of what the weather is. Coriolis effect, everybody cool with that? Raise your right hand. Not swear or anything. But we know that wind will bend like friction again makes a big deal. Why is it that you would think you jump out of an airplane? By the time you're falling, it's 700 miles an hour. Well, the only person to do that was the guy that jumped out of the Red Bull balloon out of the stratosphere. You know, I can't do it. Yeah, that's like cool. Yeah, he exceeded about 700 something miles an hour. He was about Mach 1.2. He actually broke the speed of sound. But the only reason he could is because the air was so thick. Is that?
Do you think he did?
Probably, yeah. Yeah. Now, but he was up so high, it's not that sonic wave probably would reach. But by the time he got into thicker atmosphere, he reached his terminal velocity, which is only about 120 miles an hour. Okay. Why? Because the friction of the air over his body was basically equal to his weight. So he's now not accelerating. Okay? So friction and wind friction can be really, really powerful. You guys do this stuff. I go do it in a car, 6 miles an hour. Okay, yeah. And what do you do? Your arm. Okay, yeah. So that's straight up the friction of the air. Okay, first, all of us do. Okay, yeah, everybody has. By the way, and it's the shape of a wing, right? Careful. All right. But if you do this, okay, blow your arm off. So when we talk about friction, sure enough, we talk about the air resistance. And fluid motion creates a huge amount of friction. Who is it? Jenny and Ian were talking about friction over a wing a little bit, creates static electricity. Okay. And so you don't ever want to touch an airplane or a helicopter in flight before it touches static electricity. Okay. So if you ever have to do a rescue at sea, and they put a hoist down, by the way, that hoist wire. Okay. Make sure you let the hoist touch the water before you go grabbing onto it, because all that static electricity that's in the air will discharge into your body and basically like bigger helicopters. Bigger helicopters. So, yeah. Okay. So upper level winds, definitely don't have to talk about that. The lower level winds, of course, are affected by both Coriolis effect, force, and the pressure gradients, and friction. This is, by the way, another reason that hurricanes will then break up, right, when they get over land. So we can because the air movement. Okay. All right, we talked about this. This was in the video we saw. Okay. Friction is not a factor when wind flows along the radius. Okay. But again, when friction is a factor, circular flow, rotation. Okay. And the winds, of course, will go vertically like this, right? And horizontally. So the vertical movement will create the weather. Horizontal movement will create the prevailing wind. This is why, again, right here, our weather always comes, mid-latitudes from west towards east. In fact, right now, as I watched the weather this morning, where Hillary came, all right, it really should have gone this way, right, because it was down here to the prevailing winds. But there was a system that actually allowed it to come up and go far enough north where then it did this. So guess where it's at now? It got up here, went over to Canada, and most of it is up in this area right now. So they're getting all kinds of thunderstorms up northern New York, Pennsylvania, what's left of Hillary. Okay, because it got up here and then it got stuck over to the west. Okay. All right, everybody, both vertically and horizontally understand the global prevailing winds. Okay. And again, local wind patterns, this is the last that's on your notes. Pressure, temperature, and density will change. There will be local wind patterns. Okay? And we looked at the three main wind patterns we're talking about. Land and sea breeze is one of them. Okay? And of course, if you're flying down near the beach, you got to know this stuff. It's funny because during the summertime, you'd be sitting on the beach down at Drury Beach, Carolina Beach, and you look out to behind you over the land, you see all these big, huge thunderstorms, right? And you're sitting there, man, you got a big thunderstorm over here. Why is that? That right there. Okay. That convective lifting will create all these thunderstorms inland. Okay. And then, of course, when it comes out here, the air comes down, and all the thunderstorm or whatever moisture you have will condense, or will not condense, will evaporate. Okay. And so you're cooling it off. Okay. They work on the same principle as global patterns, but again on a much smaller scale. And the ones you have to pay attention to as a pilot are the land and sea breezes, mountain breezes. That's if you're seeing it. Okay. This is what I'm talking about, right? All right. So here's your cool that comes in. As it's going up, it creates a low pressure system, so it's going to suck air in, both the warm air, right? And it's going to mix with the moist, cool air. Up it goes. Okay. We get inland thunderstorms like crazy. All right. So that's your during the day. That ain't so bad. And normally this is going to be a little bit inland. Okay, so the land, of course, has a much lower specific heat and will absorb and get rid of energy much quicker than the water. The water has a huge capacity to suck up energy without its temperature. Okay, this is why oceans actually, their temperature stays fairly, the temperature range on them is fairly low. In the temperature, it would be 85 degrees of water in the summertime. And then maybe 60, 70 in the wintertime. Okay. Now the Gulf Stream has something to do. It's just the water can suck up a lot of energy and it doesn't give up a lot of energy. Whereas the land will suck up energy fast and the temperature will go up, will drop quickly. So you get a temperature change. Heating of the day, boom, up it goes. So that's your receiver. Everybody cool with that? Where are you, as a pilot, where do you have to be careful about flying? Where would I be careful about flying? Yeah. And especially in here, you're going to get downdrafts, right? So you're going to get up and down drafts all around the place, and you want to be real careful about updrafts down as you're flying in and out of the coast. Okay? So those are your convection. It can reach up to 10 to 20 knots, and it can go up to 1,500 to 3,000. So generally, if you don't have any clouds up here, and you're above 3,000 feet, and you're probably above that convection, probably, not necessarily. Okay. So land breeze again at night, you'll get the opposite. Again, the temperature will drop on the land just a whole bunch quicker than the temperature in the water, which is maintaining fairly constant. So again, over the land, since the floor is going down, the air, it gets forced back out to sea, warms up again, goes back. Okay, so late, early to late morning, you're going to get the land. And as soon as when you get sun comes back after transition back. Okay. But either way, they are convection. And again, altitude is a little bit lower. It can reach an altitude of about 2,000 feet and between 5 and 100 nautical miles inland, depending on the temperature and pressure gradient. So, I mean, how far are we from the coast? Somebody doing that question between here and Wilmington. Yeah, about 3 hours. 150 miles. 150 miles.
Yeah, I got 110.
Yeah, 100. Okay. So yeah. So I mean, it's not going to make if it's really powerful. It might make it hard. But like if you're going down to say Elizabeth City or Elizabeth Town or Wilmington or something like that, you could run in a land breeze if you're doing a night flight down. Normally, it would be after midnight. Okay, it's usually about the 8 to midnight time frame. The temperatures are going to be pretty much equalized. So you might not even have any kind of breeze, global breeze, have other breeze, but you may not even have it land because you. All right, here's what we're talking about: valley breeze. Remember, it warms up here first. Up goes the air here, creates a low pressure system, sucks the wind right up the valley. Okay. Here's the problem with that. If that wind is going here, friction what happens on the other side. Okay. What happens if you're flying on the other side? Okay. It'll drive you right. So in this area, as air warms up during the day, air, of course, will rise from the low-lying areas up the mountains. This is known as a valley breeze. Valley breeze can go up slope 5 to 20 knots, and can be up to a few hundred feet above the ground. So if you're flying along here a valley or so, this wouldn't be so bad because you've got the updrafts there, and that would keep you up off the train. Problem on the backside. At night again, the cycle's reversed because again, you're cooling off in here, and air's going to go down the valley. And so you've got to really be careful flying around high terrain. Okay. Katabatic winds are kind of interesting. If these type of winds, if you got a prevailing wind here, a little friction happening here, they talk about it in the video as Santa Ana winds, right? But on the downside, man, you get all kinds of swirling or turbulence. In fact, if you have a mountain breeze, even hundreds of miles downwind, you'll see some sort of clouds. Right? And that is an indication that you've got a mountain breeze downwind. And it can get powerful. It can go down hundreds of miles. So if you're flying out there, you're still going to get these turbulent vortices. And if you're flying along in that area, you've got to be careful launching again in a mountainous area at that point, or downslope wind. They're going to be much stronger because basically it's the prevailing wind that's happening that is interacting with them. And they can become, if you're down in here, it can be really dangerous. Right now. Cold downslope winds again, it's cold air. Especially like if you got winds coming off, a snowy mountain, right? As the wind went over there, it was off. Okay? And so it hits the edge here and it's cold, down it goes. Okay? So it's affected by both the friction here and the temperature and the direction. So when it passes over any mountain, the leeward or downward side produces a low pressure area due to the moving air. Okay, that would be really hurt. Okay, blue guys, the same over your wing, and as you fly along, they pull the airplane up. Okay, those are Bernoulli's. Okay, that's actually Daniel Bernoulli's principle is that you accelerate fluid, you get pressure. Okay. And so if you accelerate a fluid down the slope, you can create a low pressure. And we all know that low pressure sucks. Okay? So, okay, everybody cool with that? Okay. And again, they call it Chinooks, Rockies, call it Santa Anas. Make sure you completed the guided notes at the end. And last thing I have, and if you're not going to be here, what's the last thing I have? I've got that third video, which gives you an overview of aviation weather, so we can do that. And it's 18 minutes, or 17 minutes, so it'll be just about right to get out of here. So let me start that thing. Notes, PowerPoint, there you go. All right, this one here. Last video. There you go. There we go.
Before dissipating as shown above. It begins with the cumulus stage, in which lifting action of the air begins. If sufficient moisture and instability are present, the clouds continue to increase in vertical height. Continuous, strong updrafts prohibit moisture from falling. The updraft region grows larger than the individual thermals feeding the storm. Within approximately 15 minutes, the thunderstorm reaches the mature stage, which is the most violent time period of the thunderstorm's life cycle. At this point, drops of moisture, whether rain or ice, are too heavy for the cloud to support and begin falling in the form of rain or hail. This creates a downward motion of the air. Warm, rising air, cool, precipitation-induced descending air, and violent turbulence all exist within and near the cloud. Below the cloud, the downrushing air increases surface winds and decreases the temperature. Once the vertical motion near the top of the cloud slows down, the top of the cloud.
What happens to that downward force wind or downdraft when it hits the ground? What's it going to do? Yeah, it's going to balloon outward. You ever notice when a thunderstorm's coming, just before you get there, you get all this wind and stuff at first when that's what's happening? It's down fast, and then it goes, it's got to go somewhere. It can't just stop there. Okay, so basically it comes down, and that's where you get your straight line wind damage in a thunderstorm. Okay. Everybody okay with that? And it's also where you can get wind shear on an approach as as a pilot. You really got to watch the bottom of cumulus clouds like that, or cumulonimbus clouds like that, and stay away.
Cloud spreads out and takes on an anvil-like shape. At this point, the storm enters the dissipating stage. This is when the downdrafts spread out and replace the updrafts needed to sustain the storm. It is impossible to fly over thunderstorms in light aircraft. Severe thunderstorms can punch through the tropopause and reach staggering heights of 50,000 to 60,000 feet, depending on latitude. Flying under thunderstorms can subject aircraft to rain, hail, damaging lightning, and violent turbulence. A good rule of thumb is to circumnavigate thunderstorms identified as severe or giving an intense radar echo by at least 20 nautical miles (nm), since hail may fall for miles outside the clouds.
Shell question,
If
right?
flying around a thunderstorm is not an option, stay on the ground until it passes. For aviation purposes, a ceiling is the lowest layer of clouds reported as being broken or overcast, or the vertical visibility into an obscuration like fog or haze. Clouds are reported as broken when 5/8 to 7/8 of the sky is covered with clouds. Overcast means the entire sky is covered with clouds. Current ceiling information is reported by the Aviation Routine Weather Report, METAR, and automated weather stations of various types. Closely related to cloud cover and reported ceilings is visibility information. Visibility refers to the greatest horizontal distance at which prominent objects can be viewed with the naked eye. Current visibility is also reported in METAR and other aviation weather reports, as well as by automated weather systems. Visibility information, as predicted by meteorologists, is available for a pilot during a pre-flight weather briefing. Precipitation refers to any type of water particles that form in the atmosphere and fall to the ground. It has a profound impact on flight safety. Depending on the form of precipitation, it can reduce visibility, create icing situations, and affect landing and takeoff performance of an aircraft. Precipitation occurs because water or ice particles in clouds grow in size until the atmosphere can no longer support them. It can occur in several forms as it falls toward the Earth, including drizzle, rain, ice pellets, hail, snow, and ice. Precipitation in any form poses a threat to safety of flight. Often, precipitation is accompanied by low ceilings and reduced visibility. Aircraft that have ice, snow, or frost on their surfaces must be carefully cleaned prior to beginning a flight because of the possible airflow disruption and loss of lift. Rain can contribute to water in the fuel tanks. Precipitation can create hazards on the runway surface itself, making takeoffs and landings difficult, if not impossible, due to snow, ice, or pooling water and very slick surfaces. Air masses are classified according to the regions where they originate. They are large bodies of air that take on the characteristics of the surrounding area, or source region. A source region is typically an area in which the air remains relatively stagnant for a period of days or longer. During this time of stagnation, the air mass takes on the temperature and moisture characteristics of the source region.
Okay, we're going to stop there. Because I think next they cover fronts and frontal characteristics and all that. And we're going to cover that later. One of the things that I do want you to know about, all right, is one of the things, here we go. Back here. Down here, there's a couple of Quizlets, okay? And for the first quiz, there's 57 slides. That's a lot, but anyway, you can see right here, we got the right one there. Start the magic. All right, stop it. Okay. Basically, you can click on the Quizlet. You guys are already in the class, and it's basically flip cards, which cover weather. And it's got some great information that you can flip through, and it's got pretty much everything we've talked about. And this would be a good study guide. And you can also check yourself out. You can actually do a test, your own little test, flashcards. You can do matching, learning. Yeah, there's different activities you can do with the information there. So there's a Quizlet on the atmospheric conditions. There's also, well, let me share that. Well, it didn't show up here. Hang on. Make sure it shows up here. Where'd that Quizlet go? Right there. Looks like this. There we go. And again, you can flip around on that for those. This is for my other class. Use that to get ready for the first quiz. It'll help you out. If you're a flip card studier, which I am, you know, some people like it, some people don't. You can use it or not. Up to you. All right. That pretty much covers our first notes. Everybody okay with getting your notes done? Okay. Everybody okay? Pretty much everybody got 6A done, so we're good there. I graded it, and you can look in your grade book and see how you did. I think there was only one person or two people that didn't get 100, so it's pretty close. Let me see. The 3 aviation weather videos, again, are available on the notes. And I only showed you a little bit of the Chapter 6 video, so that's available if you want to take a look at that. That's about 40 minutes, so it's a little bit long. That's why I only showed you a little bit of it. Questions on what we have covered. Make sure you know 6A, right, on your for your reading. And where'd the notes go? There we go. And Chapter 4, and that should cover everything, plus the handbook in Chapter 8. Make sure you've read that. Handbook Chapter 9. And by the way, most of that's covered in 6.8 anyway. The other ones are a little bit of a repeat. Okay, so make sure and the chapters in the weather handbook are really short. They're only about 3-4 pages, most of them. So quick reading in there, and then read 6A, and you should be good. Any questions? I think I am about done. Okay.